Thank you so much for having me. My name is Robert, and today I'm going to tell you about provably efficient machine learning for quantum many-body problems. This is a joint work with Richard Kuhn, Giacomo Torlai, Victor Albert, and John Fresco. Oops, sorry. So recently, machine learning has received a lot of attention in the quantum community. In particular, people have been interested in applying classical machine learning for quantum physics and chemistry, where the goal is to solve challenging quantum many-body problems using machine learning that could yield better solution than traditional classical algorithms. However, despite the interest, many fundamental questions remain to be answered. In particular, the key question, or you could say the key skeptics about it, is whether machine learning algorithms can be more useful than non-machine learning algorithms in solving physically relevant problems. So in this work, we will make some progress toward answering this question. So here's the outline for today's talk. I will provide a brief review on the classical shadow formalism that was proposed in a work last year. And then we will build on this classical shadow formalism to present a rigorous algorithm for training machines to predict ground states, as well as training machines to classify quantum phases of matter. So first, I will just provide some brief review on classical shadow formalism. So the key question that classical shadow formalism tried to answer is how can classical machine effectively see quantum many-body systems? So what we mean by seeing is the ability to convert the quantum system into some efficient classical representation that accurately captures many properties of the original unknown quantum system. To investigate that problem, would prove the following theorem. We showed that there exists a procedure that guarantees the following. So given two constant b and epsilon greater than 0, the procedure learns the classical representation of an unknown quantum state rho from performing b log m over epsilon squared measurement. Subsequently, given any observable O1 to OM with a norm bounded by b, this special shadow norm that we defined in the work, the procedure can use the classical representation found by step 1 to predict the expectation value of all of these observable up to epsilon error for all of these m observable. So for example, if you wanted to predict 10 to the 6 different observable with the norm bounded by 1, naively what one would do is just measure all of these observable independently. Then in that way, one would require 10 to the 6 over epsilon squared measurement to estimate the expectation value up to epsilon error. However, this theorem shows that we actually only need 6 log 10 over epsilon squared measurement in order to get the expectation value for all of them, which is a significant saving. Furthermore, this procedure is actually very easy to implement. Here's just an outline of what the procedure looks like. So it's separated into two phases. In the first phase, you gather data, which is corresponds to step 1. And then in the second phase, you make prediction. In the first phase, what you do is after getting this unknown quantum state system represented by the sphere with a bunch of atoms in it, we would apply a random unitary onto the quantum system and perform computational basis measurement. You can think of this procedure as, you can think of this high-dimensional quantum system as like the 3-dimensional object, where by performing this random unitary, you can take snapshot of this high-dimensional object in different angle, such that you can get a rough understanding of what that original quantum system looks like. And in the prediction phase, we have an algorithm based on median of means to predict the expectation value. In this work, we will focus on a particular form of classical shadow framework based on randomized Pauli measurement. So here, what we are going to do is, during this random evolution, we're going to consider tensor product of single qubit Clifford unitary, which is actually equivalent to performing randomized Pauli measurement. That is, for each qubit, you just randomly measure in X, Y, or Z basis. So now after T randomized Pauli measurement, we construct this classical shadow defined as sigma T of rho. So rho is the original unknown quantum system. And this classical shadow is just a classical representation of the unknown quantum system. And this representation is given by this formula here, which is an average over the T randomized Pauli measurement. And for each of the randomized Pauli measurement, and we will perform n-qubit experiments. So we will get n different measurement outcome. For each of the measurement outcome, we will represent it using a 2x2 matrix, and we just tensor product n of them, and then we average over the t randomized Pauli measurement to construct this sigma t of rho. So as you can see, sigma t of rho is a 2 to the n by 2 to the n random matrix. Furthermore, by virtue of the construction for how you represent this 2x2 matrix, you can make it such that the expectation value of this random matrix will be equal to the unknown quantum system rho. One of the best part of it is that actually this representation sigma t of rho only requires order of system size n times the number of randomized Pauli measurement t classical bits to represent. So you never really represent. Yeah.
Is this a sigma IT? Is it a rank 1 matrix? It's just a projector on?
Actually, it will be a rank 2 matrix. And the precise format of this 2x2 matrix is 3 times like the stabilizer that you measure minus identity. So when you write it out and when you diagonalize it, it's always look like 2 and -1. So, but the basis is essentially which basis that you measure this on. So it's not just
is this sigma t the sum? Is it like a full rank matrix or something in general?
Yes, it would be a full rank matrix, and it would not be a positive semi-definite matrix. So it's just a 2x. It's just it would just be a random matrix, and
so is the little sigma also not the sigma I is also not positive semi-definite in general?
Yes, they're not. Yeah, they're not. They're not positive semi-definite, but it's fun because yeah. So basically, what we show in this proof is that using this non-physical representation to represent your physical system rho, still preserve a lot of the key quantity that you would care about. For example, it preserves Hamiltonian expectation value, correlation functions, entanglement entropy of some constant region, as well as few body observables. So yeah, so it's a random matrix with an expectation value that's equal to rho, but there will be some large fluctuation due to the measurement, due to the statistics. And what one could show is that a lot of the property will be preserved, meaning that the fluctuation for a lot of the properties will actually be small. So this is
ask a question.
Yes.
So if rho happens to be a stabilizer state, do you get more structure from this decomposition? Do you get this typical stabilizer or Pauli decomposition?
No, you don't.
Okay.
I don't think you get that. It's something quite different from just a stabilizer decomposition of the original state rho. Okay. So, but yeah, so there's a lot of different property there's a lot of interesting property of this classical shadow representation, but what we are going to care about is that it preserves a lot of quantity, meaning that you can utilize this representation, essentially this order nt bits, to predict all of these things efficiently. So that's the main property that we're going to utilize in the following two sections. So for the second part of the talk, I would discuss a task where we wanted to train a machine to predict ground state of a new Hamiltonian. So more precisely, what we're going to consider is that we will have some parameter x that describes a Hamiltonian h of x. And what the machine has to do is, given a parameter x, it needs to be able to predict a classical representation for the ground state rho of x of h of x. So here, you should think of this parameter as an m-dimensional vector that describes, let's say, the laser intensity that controls the physical system, or maybe the few body interaction between how the atoms in the physical system interact with one another, or some external magnetic field that you applied, etc. So you should think of this parameter x as some controllable parameters that the experimentalist could utilize to change their physical system. And furthermore, because they're changing these parameters externally, we would just assume that this mapping from the parameter x to the true Hamiltonian h of x is not known exactly. So maybe they don't exactly know when they change the laser because they don't have perfect control on the laser, or they don't have perfect control on the synthesis process of this new material, etc. So we're going to assume that this mapping from the parameter x to the Hamiltonian h of x is not known exactly. And furthermore, we're going to represent any ground state rho of x on a classical computer using its classical shadow representation. So here, everything is classical. It's a classical machine learning algorithm for solving quantum problems. So more precisely, for the classical machine learning model, what it would get is it would get a set of training data telling him examples of the parameter x, like different parameter x, and the associated ground state sigma t rho of xl. So you should think of it as we have the parameter that describe a physical Hamiltonian. We probably have to first synthesize it in the lab to prepare the ground state, perform some measurement on the ground state to gather the classical representation of the ground state. We do that for a different parameter, and the collection of the parameters mapping to the classical representation of the ground state rho of xl will be the training data that will be fed into the classical machine learning algorithm. And now, after learning from this training data, what the classical machine learning algorithm has to do is, given a new parameter that's not inside the training data, so a new x, it has to predict the classical representation for the ground state corresponding to that new physical system, h of x. I hope that the task was clear. And now we're going to describe a class of machine learning algorithm that could be used to solve these kind of problems. So recall that we have a training data, which are a bunch of input parameters mapping to the classical representation. We're going to consider training a machine learning model that takes in this m-dimensional input vector x and outputs this exponentially large matrix sigma hat of x. Of course, in practice, we will, in theory, of course, we will always only consider efficient representation of this exponential size matrix, similar to like the classical shadow representation. Furthermore, we will require that the machine learning model needs to be trained within time, so as data that's polynomial in both the system size n and this m. So one example of such a machine learning model is illustrated below. So for example, let's say we consider having a huge neural network that takes in this m-dimensional vector in its first input layer, which consists of m neurons. And then in the middle, it have an infinite number of neurons in hidden layers. And finally, at the end, it would have an exponentially many neurons in the output layer. So we can actually train such a bizarrely large model in time polynomial in n and m. Basically, it's utilizing these recent development in neural network theory on neural tangent kernel. One could show that when you have such a neural network model, now you train it on this training data using this cost function. So the sum just sum over all the training data, and the sigma hat of w, so this capital W represent all the weight in the neural network. And what you're going to do is you're trying to optimize this W such that it minimizes this training cost, which is the difference between the output of the neural network and the training data corresponding to XL. We're going to consider a Frobenius norm squared. So when we consider that, one could show that the optimal, like after training, the resulting neural network has a closed form solution given by this form. So one could show that after training, when you're given a new X, the neural network, after passing this new X through the neural network, you can show that the output, like the output layer, will be equal to this formula, which is based on this learned function kappa nn that considers two parameters, that is the new input X and the training data XL. So you consider that to produce a value that's within R, so it could be positive or negative, and then it will combine all of these sigma t rho of XL, which are the training set in your training data. Furthermore, various machine learning models, including kernel methods, and also this infinite width neural network that we just described, can be shown that the global minimum of the optimization, that is after training, it has a closed form solution when you make predictions. So when you give him a new input x, it would predict that the outcome sigma hat of x is equal to this, where this kappa is the learned function for determining how one wants to extrapolate from the known examples to new examples. So an illustration is given on the bottom right. x1, x2, x3, x4 are the training data. And now, after knowing these training data, what this machine learning model would do is it would, based on this training data, figure out a learn function kappa, kind of like a metric, such that when you're given a new x, it will sort of extrapolate using this learn function from the training data to make prediction. So now, after describing this machine learning model, one could start proving things about it. Oh, no, not yet. So basically, as long as this kappa is efficiently computable, one could easily see that the output matrix, which is an exponentially large matrix, can actually be represented efficiently using only nt times capital N number of bits. So small n is system size, capital T is for each ground state, how many randomized Pauli measurement you do, and this capital N is the number of data in your training set. So now we can prove some interesting results about it. Here we're going to consider a machine learning model where this kappa is the L2 Dirichlet kernel that's often used in harmonic analysis. We're going to show that the learned function sigma hat of x would capture the ground state property accurately on average. More precisely, we proved that for any smooth class of local Hamiltonians, so h of x is the sum of local terms, that's also within some finite spatial dimension, like 2-dimension, 3-dimension, or even maybe 4-dimension, with a constant spectral gap. One could show that given a number of training data n that scales polynomially in this input vector m and independently on the system size n, and you can use a randomized Pauli measurement of only size 1 for each state, one could show that for any sum of local observables O with some bounded norm, you can use this learn function sigma hat of x to predict the property of this local observable up to some constant error. Furthermore, the training and prediction time would both be polynomial in this input vector m and linear in the system size n. So these two conditions, one could think of it as within a single quantum phase. So as long as you're within a single quantum phase, then the machine learning model could just train on polynomial size data and make prediction on the entire quantum phase space, even without knowing how x maps to h of x.
Robert, what is the norm condition on the sum of local observables exactly?
Oh, so basically it's like, essentially you should think of it as also, okay, so one thing that works is kind of like, it's just a local observable. So the L is just equal to 1, and then it can predict local observables accurately. But of course, you can also consider the situation where you have a bunch of local observable, but you should normalize it. Like for example, magnetization, it could depend on the system size. If you just sum up all the, let's say the Z operator. But what we would do is we would consider a normalized version of that. There's no sort of system size dependence, and all of these sum will be bounded by a constant.
I also have a question. So the constant spectral gap, the constant refers to the system size or x?
Constant refers to both the system size as well as this m.
Okay, but it can vary with x.
Oh, yeah, it could vary with x. It's just there's a constant. Yeah, it could vary with x.
But then it could go to 0 for certain x's also. So like.
Oh, that's what you mean.
As in, that feels like you're going through phase transitions. I don't know if that.
Yeah. So basically, I mean, it could vary with x, but as you vary within the different x, it should always be a constant bounded. Like you cannot just take it and goes to 0.
Right. So there's a bound that holds for all x, basically.
Yes. Yes.
Okay.
Yes.
Good. Okay. Thanks.
So now here are some just a very brief summary on the key steps in the proof. The actual proof is kind of long and kind of tedious. But the first step is that using this condition on having a finite spatial dimension and a constant spectral gap, you can prove certain very nice form of smoothness condition in the ground state space using spectral flow and Robinson bound. You can show that as you vary the x, the ground state will not suddenly change crazily. It would always change smoothly across the entire phase space, which is also matches the intuition of a phase. There's no sharp transition in between when you change x. So that's the first main step. And then building on that main step, you can prove a generalization error bounds for the proposed ML model with L2 Dirichlet kernel trained on this randomized measurement data. In particular, it will be a combination of statistical analysis and a realization that when you have an m-dimensional ball with a constant radius, then the number of lattice points inside that m-dimensional ball actually scales polynomially in m instead of exponentially in m. So yeah. Intuitively, one might thought that when m increases, the volume should increases exponentially, and hence the number of lattice should also increase exponentially, but actually only scales polynomially. So that fact determines the VC dimension of the proposed ML algorithm, which implies that the generalization error bounds would hold when you have a training data that scales polynomially in this input vector m. So now there's actually a very important limitation in this theorem, is that the prediction accuracy epsilon can only be a constant. More precisely, the number of training data actually scales pretty badly with the prediction error. So it's polynomial in m, but it's polynomial in m when you fix this epsilon to be a constant, but it scales like m to the 1 over epsilon. So one might wonder, so recall that all of it we're considering is a classical machine learning algorithm. You get classical data, you train a classical ML algorithm to make the prediction and so on. So one might wonder if a quantum machine learning algorithm could overcome this limitation. So in one of our appendix, we proved that actually any quantum as well as classical ML algorithm, if it just works under this very generic assumption, then it will require m to the 1 over epsilon amount of training data. So the advantage in this very general problem, can only be polynomial. So now we also present another result. So recall that we talked a little bit about the classical ML setting. We talked quite a bit about the classical ML setting, briefly about quantum ML. And now what if we utilize a classical polynomial time randomized algorithm with a full knowledge on what the Hamiltonian is to try to solve this problem? So one could show using some standard results in complexity theory that if you wanted to have a polynomial time randomized algorithm that could make prediction of one local observable O, like an average prediction over this X for any one local observable O in any smooth class of local Hamiltonians in a 2-dimension with a constant spectral gap. So basically the condition is, the task is simpler than the theorem because the previous theorem works for any local observable and it works for any finite spatial dimension, but here we just focus on 2-dimension and one local observable. And then the prediction error is also set to 1 over 4. One could show that if such an algorithm exists that could achieve this, then RP would be equal to NP, meaning that NP complete problems can be solved in randomized polynomial time. And as you can see, this proposition shows that when you have a non-machine learning algorithm, it cannot achieve the same guarantee as the machine learning algorithm that we show in Theorem 1. So going back to our initial question on whether and why can machine learning be more useful than non-machine learning algorithm, the combination of Theorem 1 and Proposition 1 gives us a concrete answer. Basically shows that machine learning algorithm could solve certain challenging problems that non-machine learning algorithm could not solve. And the basic intuition behind this is that when you utilize a machine learning algorithm to perform such a task, what it has to do is it just has to generalize from the data. It just have to try to find a good way of extrapolating from the data. And that could be much, much easier than computing everything from scratch, especially since here you can consider the setting where the machine learning model just gathered the data by performing physical experiments, where nature could serve as like a quantum computer that provides certain computational power that enables the machine learning model to build on top of it. So now, after discussing the theory part, we would like to also see how well this classical machine learning algorithm perform in practice. Oops, sorry. So here is an example where we consider a one-dimensional Rydberg atom array. We consider a training data of size 20 with 500 randomized measurement for each of the training data for constructing this classical shadow. And we consider the best ML model chosen from Gaussian kernel method, L2 Dirichlet kernel, as well as infinite width neural network. So figure A just provides some more detail about Rydberg atom array. Figure B shows that there's actually 3 phases when we vary the parameters. So we only consider 2 parameters here, the detuning and the interaction range. And then it would generate like this phase diagram with 3 different phases. And while our theorem only shows that it works when you consider a single phase, the numerics suggest something stronger, showing that even when there's like 3 different phases in your parameter space, the classical ML model could still predict accurately like all these local properties, like the expectation value of X, the expectation value of Z, etc. We also compare it with a very naive method where you just output the prediction using the closest training data. Like for example, for this point, star, we just predict the ground state as the same as this point. And you can see that it, in general, this performs much worse than when you actually train this classical ML model, meaning that classical machine learning can indeed find a better way of extrapolating rather than just using the nearest training data. And similar things could be seen from the theorem. If you just utilize that very simple algorithm that pick the right one, you don't get the theorem. It's just not going to work. And the numerics also verifies that. Now for 2-dimensional random Heisenberg, so here we also consider a 2-dimensional example where we have a 2-dimensional anti-ferromagnetic random Heisenberg model with now the number of parameters is much greater. It depends, the number of parameters scales linearly in system size for this example. And hence we consider a slightly bigger training set. We consider 100 different Hamiltonian parameters and train this classical ML model. And you can also see that from figure B, the prediction from the classical ML model accurately follows this very time-consuming DMRG. So essentially, if you apply DMRG for 2D system, it scales exponentially in like the width of the system. So it's kind of brute force way of doing it, but you can see that the prediction using classical ML is also very accurate. So now that concludes the second part of the talk, where we give rigorous theorem showing that classical machine learning model can predict ground state accurately, and we provide some numerical experiments to verify this claim. Now for the final part of the talk, we will consider training machines to classify quantum phases of matter. Here, the task is simpler. Basically, what we wanted to do is, given a quantum state, we wanted to predict which quantum phases of matter the state is in. It's in the trivial phase, it's in the symmetry broken phase, it's in the topological phase, etc. Again, we are going to represent the quantum state rho using the classical shadow representation, which is this 2-dimensional array consisting of this 2x2 matrix sigma ti, where t goes from 1 to capital T and I goes from 1 to small n, which is the system size. And here, what we're going to consider is that the classical machine learning model will be given a training set telling him that for this classical representation, it corresponds to the trivial state. For that classical representation, it corresponds to topological phase, and so on. And now, given a new state, not in the training data, the classical ML model has to classify which phase this new state is in accurately. So essentially, what the machine learning model has to do is it has to find a classifying function that separates different phases of matter in the most reasonable way. So for example, for a symmetry broken phase, there's typically a local observable that could be used to distinguish between two phases. So like for states in phase A, it's greater than 0, but for states in phase B, it's less than or equal to 0. Here, it's much simpler in the sense that the classical ML model only needs to learn some linear function, which can be done using some linear classifiers to classify between different symmetry broken phases. However, if one wants to utilize the same linear classifier for classifying more exotic quantum phases of matter, such as topological phase, proposition 2 shows that it is deemed to fail. Basically, one could prove that when there's two distinct topological phases A and B, we can show that there's no observable, not even global one, that acts non-trivially on all the qubits. There's no observable that exists such that it could linearly separate between phase A and phase B. So what that means is we need to find a more powerful machine learning model that can learn nonlinear function, such as trace of O rho tensor rho, trace of O rho tensor power to D, or a more generic analytic function. So what we're going to do is we're going to consider this kernel trick that's often utilized. For example, in this quantum kernel method, we're going to consider, but here it's all classical, so it's a classical method. So what we're going to consider is learning a linear function in an infinite dimensional space where we map each of the state rho into this infinite dimensional vector. More precisely, we first utilize this randomized measurement to map the state rho into a classical representation ST of rho. And then we map that classical representation to an infinite dimensional vector represented as follows. So it's a kind of a crazy formula, but intuitively one can understand it as follows. So the most inner part is essentially utilizing classical shadow formalism to provide an approximate reduced density matrix for a subsystem consisting of qubits I1 to IR. And then we just concatenate over all possible R-body subsystem. So now, it's a very long vector. And now we concatenate over all sizes of subsystems. So now it's an even longer vector. We take a degree D polynomial expansion of that high dimensional vector, which enables it to learn non-linear functions like trace of O rho tensor D. And then we concatenate all degree. So now it's an infinite dimensional vector. And what we're going to do is we're going to learn a linear function in this infinite dimensional vector, which will correspond to learning some highly nonlinear functions, such as an analytic function of the original quantum state rho. So basically, this is the proposed classical machine learning algorithm for classifying quantum phases. And one could efficiently train such an infinitely large model as long as one could efficiently compute the inner product between these two infinite dimensional vector phi shadow of ST. By just doing some Taylor expansion, one could show that we can map this take the inner product of the infinite dimensional vector into this closed form that could be evaluated in time, linear in system size, and quadratic in the number of Pauli measurement that one performed. And we will refer to it as the shadow kernel because it's some kernel function between the classical representation of rho and the classical representation of rho tilde. Utilizing this shadow kernel, one could show that training this classical machine learning model only takes time polynomial in system size, in the number of randomized Pauli measurement, capital T, and training size, capital N. And it's very, very efficient in practice.
Do you really need these infinite dimensions?
Sorry?
If you use the Taylor expansion, sure, they pop up, but do you in the end only work over, I mean, how many inner products do you need to take? Can't you reduce to a finite dimensional subspace somewhere?
Oh, so basically, you only need to take inner product between all pairs of training data.
Yeah, okay, so that tells you the dimension you're really working over, right?
That is true. That is true. You're actually only working over this the space spanned by your training data. So it's not. Yeah. That's a great question.
But it has a
the
funny
nice thing
inner
about
product.
it. Yeah, sorry.
No, I was just saying it has a funny inner product, which I guess is motivated by the embedding, right?
Yes. It's more like I first constructed this embedding, and then I take the inner product, which results in this kind of slightly strange form.
And sorry, is there, by any chance, is there a physical interpretation of this huge direct sum decomposition? So you see these things in like box spaces, but I don't know if there's any relationship. Not that I know.
Oh, I'm not entirely sure, but the idea here is pretty brute force in the sense that we just include all possible reduced density matrices into this infinite dimensional vector. We also weighted it. So we weighted according to sort of how complicated it is. Like if you consider higher degree functions, then we will weighted it like we have this decay, which corresponds to saying that the higher degree function, you should like basically it will be less likely to utilize this higher degree function because its weight is smaller and stuff like that. So
but these weights, they come from the exponential function, no?
Yes, they're essentially there in order for you to end up at the exponential function. But there's also like a more mechanistic interpretation of these, in the sense that one could prove that what the machine learning model would do is essentially it would first focus on using low degree and few body functions. And if it couldn't find a good separating hyperplane in that region, it would go to more complicated, like higher degree or higher body function. So this weight actually have a mechanistic interpretation in practice. And it would actually reveal itself when we try to prove this theorem shown here. So basically one could show that if there exists some nonlinear function of few body reduced density matrices that could classify the phases, then the classical algorithm, this machine learning algorithm that we devised previously, can learn to classify these phases accurately. And the amount of training data and computation time with both scales polynomially in the system size. Furthermore, the machine learning algorithm will construct this classifying function explicitly, so you can often just look at what it constructed and try to make sense of what is the right structure for classifying these different quantum phases. So some examples of classifying functions on few body reduced density matrices are given below. So all of it, we're going to assume a constant spectral gap similar to theorem 1. If you assume a constant spectral gap, then for example, you can show that if you wanted to classify a 1D Haldane phase from a 1D trivial phase with this O2 symmetry, then you can utilize a twist operator that only acts on few body, and it's just actually a linear observable to classify between this 1D Haldane phase and 1D trivial phase. On the other hand, there are other examples. For example, if you consider Hall conductivity for systems that's adiabatically connected to free fermion, there's an old paper by Alexei Kitav showing that there exists some low degree polynomial. Actually, I think it's like degree 3 polynomial on 6 body terms that could be used to classify, to estimate the Hall conductivity, essentially classifying between the trivial and some other SPD phases. Another example is topological entanglement entropy. Now, this is just a nonlinear function, but it's actually also fine. When you have a constant spectral gap, the correlation length will be constant. And in that case, you only need to compute the topological entanglement entropy in a constant region in order to classify between topological phase and the trivial phase. And basically what theorem 2 shows is that as long as such a classifying function exists, the machine learning model, this classical machine learning model using shadow kernel, is guaranteed to find it. So that's also look at how well it performs in practice. So here we consider a one-dimensional symmetry protected topological phase. We're going to perform 500 randomized measurements to construct classical shadow for each state. And we're actually going to consider an unsupervised version of the proposed method. Essentially, we're going to consider using this kernel PCA based on this shadow kernel. So what it does is this shadow kernel maps all the state into this infinite dimensional vector. What kernel PCA does is it will try to find a low dimensional vector, like 1 dimension or 2 dimension, such that everything is maximally separated in that low dimensional place. So here in figure C and D, we consider two different slices on this phase diagram. So figure C consider this slice, which consists of two phases, and figure D consists of this slice, which consists of three different phases. And you can see that without any label training data, you just give the unsupervised machine learning model all these states, it immediately figures out that these are the trivial phase, and these are the trivial states, and these are the topological states. And for states that are on the boundary of the space transition, it could also figure out you can also immediately see them, which are placed at a higher point here. And in figure D, there are three different phases. And you can also see that the unsupervised machine learning model can accurately place these three different phases without any label training data. So of course, if you provide some label, like you provide a single point here, a single point there, and a single point there, you can easily see that if you consider a supervised version of the shadow kernel, then it would easily classify between the three different phases. Similar situation also holds for two-dimensional topologically ordered phase. Here we are going to consider a topological phase formed by torical ground state, which adding some short-range fluctuation by applying some random, like constant depth random circuit. We're also going to consider a trivial phase, which is the product state where we apply some constant depth random circuit on top. Here we're going to consider a torical with a codistance of 10, which corresponds to like 200 qubits. And figure B is this one-dimensional representation found by this unsupervised machine learning model. The x-axis is the circuit depth. When the circuit depth is low, you can see that the machine learning model can accurately label them and separate the trivial phase from topological phase. But as the circuit depth increases and approaches this code distance, the two phases actually start to become indistinguishable from one another, because if you just apply a huge random circuit, the two phases will collapse onto one another. And this is also what the machine learning model found without any information. So finally, in figure C, we consider the true classification accuracy. That is, after performing this unsupervised machine learning model or some other supervised machine learning model, we test its classifying accuracy when it's presented with a new input state. So the green one is this unsupervised machine learning model performance. You can see that when the circuit depth is small, it's perfect, but then it degrades as the circuit depths become too high. We also compare it with a traditional, with a state-of-the-art method that people have considered before, which is feeding in some classical data into a convolution neural network. So there, what's happening is one could show that this convolution neural network will always be learning some observable to classify between the two phases. And as we have proven in proposition 2, there's no observable that could be used to classify between topological phases. So as you can see, this convolution neural network method is the same as random guessing when there's a single circuit depth. For zero circuit depth, it can find an observable. Basically, it just finds a stabilizer for toric code, and it could be used to classify between a product state and a toric ground state. But when we just add in one layer, it would just go to 0.5 accuracy, which is the same as random guessing. So now to conclude, we proved that classical machine learning algorithms informed by data from physical experiments can effectively address some quantum many-body problems. And as a consequence of that, we established the advantage of using classical machine learning models over classical non-machine learning models in a physically relevant task. So some of the open questions are as follows. So for example, could one prove advantage of machine learning over non-machine learning algorithms in other kinds of tasks? The second question, can we build on top of this to provide rigorous guarantee for other quantum problems with classical ML? And finally, people have been interested in using quantum machine learning model to solve quantum many-body problems. But here we have mostly shown that in these problems that we study, classical machine learning models can already be very accurate. It comes with rigorous guarantee, and it works really well in practice. So could we actually construct a useful class of quantum learning problems that exhibits exponential quantum advantage? So that's it for my talk. Thank you so much for listening.